So again, we're going to try and push this book along the ceiling of our classroom. We're going to press with a force of 20 newtons. And the book slides along the ceiling with a velocity of 2 meters per second. I'd like you to find the normal force and frictional force acting on the book. All right? So I'll say all the details again. We're going to push a book along the ceiling of the classroom using a 20 Newton force, angled at 30 degrees from the vertical. The book slides at a constant speed of 2 meters per second across the ceiling. I'd like you to find the size of the frictional force, and I'd like you to find the size of the normal force acting on the book. All right, we have a set of 4 steps to try and help us solve these problems, but we all know that some of these steps have more things to do than others, correct? Yes. So let's start with the first step. Do we think this is a first law problem or a second law problem? This is clearly a first law problem. Very good. The book is sliding at a constant speed, so the net force acting on the book is 0. Excellent. We're now going to draw a free body diagram that can be used to help us figure out what's happening to the book. So I'm going to start by reducing all the forces acting on my system, the mass of the book down to a dot so I can represent all the forces acting on my system. I need to draw these forces so that they are an arrow that starts from the center of the object and is directed away from the object. I have a set of basically 3 categories of forces that we apply to this. Fundamental forces, contact forces that include pushing and pulling, and then resistive forces. That's basically the couple of different types of forces that we have. Are there any fundamental forces acting on the book? Yes. Yes, most certainly. So this is the easy stuff, kind of that, I call it the low-hanging fruit, easy to grab these. So I will draw a downward force, and I know a little bit about this force. I know it's going to be 15 newtons long because it's a 1.5 kilogram book, and the weight of the book is mg. So as I look at the size of that arrow, I'm trying to remember, I'm going to have to draw another one that's 20 units long in a minute. I should be cognizant and aware of the direction and size of the arrows. All right. Is there any ropes, strings, or anything else connected to the book? No. So I'm going to have no tension forces acting on the book. Is the book in contact with any surface? Yes. So I now have to draw a force considered a normal force. That will have to be perpendicular to the surface. What direction is that arrow going to be? It will be straight down. The ceiling does not pull up on the book. It pushes down on the book, perpendicular to the surface. That the only way it can push is downwards. So I'm going to draw another arrow in the downwards direction. Now, you have choices about how you draw this arrow. Some people like to draw them stacked like this. I generally don't, but this is purely fine. I tend to like to have the forces drawn side by side. So I will tend to draw it like this. Neither is correct or incorrect. They're both just fine. Sorry, neither is incorrect. They're both correct. So I tend to draw the forces side by side. Now, is there any other forces acting on the book? Yes. Yeah, there's another contact force. I don't have a good name for it. I don't have to. They are telling me that there is a force that is 20 newtons angled 30 degrees from the vertical. You can call it an applied force or something if you want, but if they give you a force to use, you must use it. Do you understand? Yeah. So, unfortunately, you can't draw it like this. So what you have to do is push it through and draw it like that. Do you understand? Because all the forces have to start from the dot and be drawn away. So when I draw this in here, I'm going to start from the dot and draw it away from the dot. Something like that. Now, I hate doing this because it insults your intelligence, but sometimes you need this, and this is one of those times. Figure out where that angle goes. Does that help you figure out where the angle goes? We know that this angle and this angle must be congruent because they are vertical angles. Sound familiar from your freshman year in geometry? So my expectation is that you know that the 30 degrees is going to be somewhere over here. I expect that you can do geometry. Are there any other forces acting on the book?
Yeah.
Does this look balanced to you? It might be balanced up and down, but does not look balanced left to right to me. Does it look balanced left to right to you? There must be something acting to the left to provide balance. This is a net force equals 0 problem. What other force could possibly be acting to prevent the book from accelerating? I think friction's probably a very likely force here. And yeah, this would be kinetic friction because it's sliding. So friction is a force that prevents one surface from sliding past the other. But what maybe you don't know is that the frictional force must be drawn parallel to the surface causing it and perpendicular to the normal force causing it. So that means friction must be directed this way. It's parallel to the ceiling and perpendicular to the normal force. I believe we have captured all the forces that are acting on our system. We have a free body diagram that describes it. Are there any questions? If asked to draw a free body diagram, this is what you draw, and this is it. At this point, the free body diagram is done. So if you're being graded on your free body diagram, you must leave it here. Does everybody understand? But I don't think you can solve the problem leaving it here. So you may have to draw another diagram, something else that you can use to assist you in solving the question, which is what the whole rest of the free body diagram thing is about, applying a coordinate system and breaking off-axis forces into components, which is what we're going to do here. Now, when it comes to a coordinate system, we can choose any coordinate system we want for any problem. But if you want to make it easier to solve, your highest priority is to align it with the direction of the acceleration. Is this object accelerating? No. So I don't have to make that my highest priority. Next priority is to try and align the coordinate system with as many forces as possible. Well, it seems to me that 3 of these forces are already perpendicular to each other or aligned with each other. Seems like that would be the best way to utilize X and Y. So that's what I'm going to do. I'm going to choose an X direction and a Y direction that are aligned with the most number of forces possible. Go ahead and decide what direction are you going to make positive. Now, we clearly have a force that is not in the X or Y direction, right? We are going to have to break that force up into components, which means we're going to add arrows to this diagram. This is where you will lose credit if this is what you're being graded on for your free body diagram, because it will say not to add components. But we're going to add components. So let's talk about the components here. I'm going to try and break up this 20 Newton force into a component aligned with the Y direction and a component aligned with the X direction. When drawing components, they must be aligned with your choice for X and Y. So for this, that means I'm going to have a portion of the 20 Newton force in the Y direction and a portion of that 20 Newton force in the X direction. Now, knowing my trig, this is 20 sine 30, and this one is 20 cosine 30. Any questions about that? Now, what's important is that once you have broken your force up into its components, those components take over for the force that was there. They represent it. So you don't need that one. And what we are left with are forces that are all aligned with the X and Y direction. Now we can go on to step 3 and apply Newton's laws to our problem. Now, to do so, we have to break this up into the net force, net force in the x direction, which equals 0, and the net force in the y direction, which also equals 0. In the x direction, I see two forces. I see 20 sine 30 and friction. Once I've gotten them all, I've gotten all the forces, I set them equal to 0. In the y direction, I see 20 cosine 30, normal force in the negative direction, and weight in the negative direction. That equals 0. Now, this is what I will expect you to do tomorrow. I'll expect you to make it to this point. This is what you will turn in, showing that you can make it through all first 3 steps. You don't have to solve the problem. You don't have to give me a numerical answer. I want to see a free body diagram, and I want to see these net force equations with you appropriately breaking out your force into its components and then subbing into a relationship. Everybody got it? Any questions about that? Yep.
When you were talking about friction, you said...
There's clearly a pathway. I mean, this one can be solved right now for the frictional force. And if you do a substitution of mg and for weight, then this one can be solved for the normal force. Right? So when we talk about step 4, solving your problem, there might be substitutions. There might be that you have to bring something else to the table, like weight equals mg. You might have to do more trig, but there's going to be a way for you to take this information and then solve for something. But you don't have to know what you're solving for to analyze the problem. So we're going to do another example. You guys good for it? Yeah. All right. So let me set up this next example. So I have a truck. It's going to be accelerating to the right. Accelerates to 2.5 meters per second squared. Truck has a mass of 2,200 kilograms. The engine supplies a constant force to the truck to the right of 7,000 newtons. And the truck engine supplies a constant force to the truck to the right of 7,000 newtons. What is the size of the resistive force acting on the truck? And what is the net force acting on the truck? Again, what is the size of the resistive force acting on the truck? And what is the size of the net force acting on the truck? Everybody got the details?
No. Can you repeat what you said about the engine?
The engine applies a force of 700 newtons to the truck to the right. Truck has a mass of 2,200 kilograms. 7,000 newtons. Try it. I don't think you need me for this one. Bunch of forces acting there, figure them out. Think you can do it. Let's start at the beginning of this problem. Is the first law problem or a second law problem? So I'm going to start by saying net force equals ma. Well, right there's your answer for net force, right? Net force equals ma. You have m, you have a. 220 times 2.5. That's your net force. I want to be really clear. Net force is equal to ma. So there's there's very little work to be done there. If you have both the mass and the acceleration, you have the net force. Now, yeah, if you didn't have acceleration, you might have to add up all the forces. But in this case, you had the net force from the start. Everybody understand that? All right, so we can move on from there, but that's where you get the 5,500. So net force equaled 5,500 newtons. But the other question, the resistive force, that's going to take some work. I'm going to start by taking my object and reducing it down to a point. I'm going to ask myself if there's any fundamental forces acting on the object. The answer is yes. In fact, I'm pretty aware, as are you, that it's probably a downwards arrow. That's going to be pretty big, right? 22,000 units long. But that's going to be the weight of the truck. Are there any pulling or pushing forces acting on the truck? Yeah, I'm pretty sure it's in contact with the floor. That's going to be a pushing force. What kind of force? Normal. So I'm going to draw an upwards arrow to indicate that there's a normal force acting on the truck. And since I think it's the only thing acting upwards on the truck, I'm going to try and make that arrow the same size as the weight. We were told a force was acting on the truck, weren't we? 7,000 newtons acting to push the truck, I assume, forwards. So I don't have a name for this. I don't have to. It's 7,000 newtons to the right. There's no force called a resistive force in your list of forces, is there? You're probably going to have to use your analytical brain for this. What is the likely direction of a resistive force acting on a truck trying to go to the right? Okay. There we go. It is sometimes, like I said, there might be forces to which we don't have a name, but we still have to come up with a way of dealing with them. So I'm going to put F sub R, resistive force. Combination probably of friction and air resistance, stuff like that. Now, I'm kind of fortunate all these forces are already, in cardinal directions, but we do have to decide our coordinate system for this. And by definition, I said to line up the coordinate system in such a way as to be aligned with the direction of the acceleration first. Make that your first or highest priority. It's accelerating to the right, so I want the positive x direction to be to the right. Positive x direction. And that means positive y will have to be that direction. I now need to take my second law here and break it up into two parts. One in the x direction, one in the y direction. Because there's no off-axis forces for me to deal with here. So net force in the x direction and net force in the y direction. I had a lot of questions about this, but this one's MA and this one's 0. Do I have any questions about that? Oh, good. Good. Well, that means that 7,000 minus FR equals MA. Add up all the forces in the x direction, which means 7,000 is in the positive direction, FR is in the negative direction. Add them up, set them equal to MA. And then normal minus weight equals 0. Again, I expect you all to get this far tomorrow. Any questions about this part? Now you could go further than this. You could have found the resistive force. Right? We have M, we have A. So we could have taken this function that we created and said 7,000 minus FR equals 2,200 times 10. I'm sorry, times 2.5. 10. Use that to figure out what the size of the resistive force is. Right? That's the analysis part. That's solving the problem using what we developed. Try again? Oh yeah, most definitely. Let's increase the level of difficulty. Don't know about you guys, but every once in a while, I have to break out of one of these. And mow the lawn. So, So I am going to take my lawnmower and I have a push mower. I don't need one with assistance. I'm not a weenie. I can push it. So if those of you need one of those ones that pushes it for you, come on, gut up, do some work. Let's say that the lawnmower has a mass of, I don't know, mine's not particularly heavy. We'll go with, I'll go with 20 kilograms. And we are going to cause it to accelerate this way. Not particularly fast. I won't cut the grass. At 0.5 meters per second squared. With a pushing force of 30 newtons. I mean, I could push it harder, but I don't have to. Angle of, say, 40 degrees. Give me just one sec. Let me make sure my numbers are going to work. All right. I'd like the size of the frictional force and the size of the normal force acting on the lawnmower. Everybody got it? Size of the frictional force, size of the normal force acting on the lawnmower. Has anybody actually mowed the lawn before? Okay, so this doesn't actually go the way we say. Usually you push this way on the handle and you use the weight of it to keep the lawnmower down. We are not doing that. We're saying we're pushing down the handle like an idiot would. Okay? That's your problem. Everybody got it? Good, good. We're gonna mow like an idiot. All right. So let's walk through. Again, the frictional force like 13 and the normal force like 220. Let's see if we can't finish this. I'm gonna start by recognizing this is a Newton's second law problem. I know that because it's accelerating. I gave you the acceleration. So I know the forces are unbalanced. Next, I'm going to indicate all the forces that are acting on the object. I'm going to start with a free body diagram that has a downwards arrow representing the weight of the lawnmower. Now, there's an applied force given to me. The weight of the lawnmower is 200, the applied force is 30, but based on where the angle is, I'm gonna have a force that is in this direction, less than the weight of the lawnmower, but at an angle of 40 degrees from the horizontal. It's a 30 Newton force. Now I'm looking at how much of that force is to the right and how much of that force is downwards, and it's making me think that there's got to be a normal force that is greater than the weight because I'm pushing downwards into the ground, ramping up the size of the normal force. And lastly, I'm pretty sure we've got a frictional force this way, but that frictional force has got to be less than the sideways part of that 30 Newton force, or it wouldn't be able to accelerate. I believe these are the forces that are acting on my system. Any questions? This would be a free body diagram. You would turn this in. But we're going to work on it. So we're going to extend this. And I'm going to decide a coordinate system. And to me, the highest priority is to align the coordinate system with the direction of the acceleration. It accelerates to the right. So I want my positive direction to be to the right. So I'm going to make this positive x. That makes this direction positive y. I notice I'm going to have to take a force and break it up into its components. There's going to be a component of this force in the x direction and a component of this force in the y direction. In the x direction, I've got 30 cosine 40. In the y direction, I have 30 sine 40. Those are my two components. Once I have them, I can ignore the 30. Because these take over and totally represent the force that was there before. So now, net force in the x direction, net force in the y direction. Which one of these is MA? X direction. The other one is 0. So I have 30 cosine 40 minus friction equals MA. I have normal minus weight minus 30 sine 40 equals 0. This is where I'm expecting you to go tomorrow. I expect this level of work in less than 10 minutes. Now you can answer this, right? We can right here, we can solve this pretty quick. A little substitution, right? Mass is 20, acceleration 0.5, you plug them in, solve for F. Here, we know that weight's gonna be mg. There's a solution here to figuring out normal force and frictional force. But you are packing, so I guess that's a sign to me that we are. So, sine of 40 has to be opposite. Whatever this so-called is. Opposite over 30, right?
Yeah.
So when I solve for opposite, I get 30 sine 40.
Okay.
Is that good?
Yeah, thank you.